All right, the number E. This is not a typo. E is indeed a number. And we'll talk about that a little bit later on in these here notes. First of all, this front page, you might be familiar. This is what we did on the in-class worksheet. One of the things that we need to be able to do is solve a problem where you're trying to find t. Now, we don't have a way to solve algebraically when t or x is the exponent. The only way that we can solve a problem like this is by graphing. And in class today, we did a window of 300,000 was all the way up here, and then so that would be, this was our 250,000, and then this part of the equation was our income as it went up. I think I went out to about 50. You find this intersection point, and you should have got 30.5 years. It would take 30.5 years to grow $22,000 to $250,000. And then we did an interesting problem where we took $1,000 and we compared how compounding it at different times or different number of times changed the outcome of our money in 1 year. So after 1 year, if we compound it annually, if we do it once a year, we take $1,000 at 10% of 1,000 is 100. So the bank would give us $100 plus our original 1,000, so we'd have 1,100. If you do it monthly, where they give you one piece of your 10% each month, you'd get a little bit more, not much more, but $4 more. And then weekly, you'd get a little bit, not quite $1 more. Actually, you would get, 30-some cents more. You would get 9 months more if they did it daily, 9 cents more if they did it daily, 2 cents more if they did it hourly, and if they did it every single second. So if they took your 10% and every second they gave you one little teeny tiny piece of it, you would get the same amount as if you got hourly. So that's interesting, right there. What happened here? What happened is it leveled out. It leveled out. It approached 1105.17, and then it just stopped, right? No matter, even if we compounded it more, we wouldn't get more money. It kept rising. We kept getting a little bit more, but at some point it maxed out. And there was a let's go to page 2. There was a mathematician named Euler. I know it's a weird way to say this word, but Euler is arguably the greatest mathematician of all time. He looked at this problem here. 1 plus 1 divided by n raised to the n power. Quantity to the n power. Now, when we have 1 plus something, that was an exponential growth problem, right? So 1 plus this thing here, this is a growth factor. And when it was raised to the n power, as n got bigger and bigger, remember the graph grew very fast. Remember when we were folding paper, it grows very, very quickly. However, 1 divided by n, as n gets bigger and bigger here, what happens? As n gets bigger and bigger and bigger, for example, 1 divided by 1 is 1. But then if you have 1 divided by 2, that's a half. And then divided by 4, you get 1/4, a tenth, you get 1/10, so on and so forth. So as n gets bigger here, this whole thing here actually gets smaller, but it only approaches 0. It gets smaller, approaches 0. So 1 plus, as we get closer and closer to 1 here, and this gets bigger and bigger and bigger, what happens? And an interesting thing happens. So if you put this into your calculator, you would have 1 plus 1 divided by 10 to the first power, close parentheses, raised to the, and it's always a good idea to put parentheses around your exponent as well, 10 to the first power, to the first power. And what Euler found is he got 2.5937. Let me change this really quick. And then if you press second enter, change those ones, those 1 exponents, to 2. Remember, there's 2 of those ends. There we go. And you get 2.7048. Right? So 10 to the 1 is 10. So if you do 1 plus 1/10 raised to the 10th power, you get this number. But then 1 plus 1 divided by 100 raised to the 100th power, that's a whole bunch of them, right? It's a little bit bigger, but it's still 2-ish. All right? And then if you do second enter and change that those 2's to a 3's, I kind of worked this out ahead, so you can check me if you like, but I got 2.7169. So that's to the 1,000th power. To the 10,000th power, you get 2.7181. Oops. And then 10 to the 5th, which is the 100,000th power, you should get 2.7183. So look at this. It keeps getting bigger and bigger and bigger, but it starts 2.5 became 2.7. And 2.70 became 2.71. 2.716 went to 8. It's approaching this number. So what we got here is 1 plus approach 0 raised to, and this approaches infinity, right? Is the more and more that we get, it approaches this weird number. And your calculator is actually familiar with the number e. If you press second and then divide by, you'll see that e right there. E is the point. The big long number is 2.7182 or 83 if we round it, but it keeps going on. This is actually another irrational number. 2.7183. I'm just only going to go to the 4 decimal places. This is an irrational number, much like pi. And it's actually a really important number. First thing that we're going to do with e is we're just going to do some exponent problems with e. E, it can be treated like a variable, but at the end it can also be a number as well. So here, e times e to the 3rd times e to the 4th is e to the 7th. Simple ones like this. Why don't you pause it and hook up the first 4, and we'll talk about the 5th one. All right, so hopefully here 16 breaks down to 4 and 4. 4, 2, so a 2 comes out. Now, this is, again, this is 16 to the 1/4 power and e to the 8x times 1/4 power. So 8x times 1/4 is e to the 2x power. Sure got that. This one, 10/25 reduces to 2/5. E's, who wins? Top wins by 1. There's that one. Then here, this would be 9 e to the negative 8x, but to have a negative exponent is not cool, so this is 9 over e to the 8x power. Then number 5, since this is a 0.06, you know, this is of course 1 divided by e to the 0.06 power, but it's got the squiggly line approximate. Go ahead and put this in your calculator. You could put it in as e to the, now you'll see right here if you go second and then this thing called ln, and we'll learn about that after spring break. E to the negative 0.06, and you'll get approximately 0.9418. 0.9418. E is a value. It's a weird value. Do I expect you to memorize what E is approximately? No, I don't even care. If, you know, because I know that your calculator knows it. Maybe in February we should have E Day, right? Oh, but that's the problem. There's not 71 days in February. Anyways, continuous interest. Think about this. Back at the beginning of the lesson, we talked about If we compounded our interest yearly, annually, monthly, daily, hourly, and every second, what if we did it nonstop, even more nonstop than every second? What if we did it continuously, where we never stop, just every gazillion seconds we would give you some interest? Continuous interest is A, the amount in the account equals P times E to the RT power. All right, now this is a new bank formula problem, just like A equals P times 1 plus R divided by N raised to the NT power. These do the same thing. You use this one when it's continuous. You use this one for every other passage of time. Seconds, months, days, monthly, quarterly, what have you. All right, for every other value event. But if it's continuous, you're going to use this one. So our girl Gertrude invests in a bank that offers 9% interest compounded annually, or compounded continuously. How much will she have after 14 years? So A equals the principal, 1,000, that's our starting amount, times E raised to the 0.09 times T, 14. So bust out our handy dandy calculator, and we're just going to put this straight in. 1,000. Oops. Times E to the, I notice it's got parentheses for us, that's nice of them, 0.09 times 14. Oh, you could do second and use this E and raise it to a whatever power, but then you got to make sure you put your own parentheses. Then close this one. You should get approximately $3,525.42. All right, the number E. The biggest application of E is this continuous interest. Other than that, it's just a unique number that we'll actually talk a little bit more about later.